let's see, mass moment of inertias. So what the next thing we got to do is we've got to start figuring out what are these inertias and how do they react, or how are they looked at from the motor's perspective. So let's say we did that same system that we did before. I'm trying to decide here if it's too complicated for the first pass through this. Yeah, it's too complicated because it's got linear to rotary translation. Let's just stick to the simplest kind of motor loads are when you have a rotary motor turning and the end result is a rotary load. Okay, so for instance, let's draw a little system on here. Let's say that we have a robot arm. All right, you guys all like designing robots, right? Why not? So let's say we have a robot arm, and now we're going to start the procedure that you would need to do to get your motor sizing checked. This is essentially what you do, and this is a fairly simple system. The reason you're even here learning about motor sizing instead of just going and downloading some software is kind of because of this, because you have a bunch of terms to solve and there's a lot of design decisions that you have to make along the way, but there really isn't that great a software for you to, SolidWorks doesn't have a motor sizing module, does it? Right? Why not? Why doesn't, why can't you do this why can't you do motor sizing in SolidWorks? They know, the inertias, the mechanisms. All you have to do is look at the motion profile and assign some frictions. Sure seems like a thing to me, but it's not. So where is it? Manufacturers, sometimes they'll put out a motor sizing program. The trouble with those is now you're taking your design that's over here in SolidWorks and you have to essentially recreate the whole thing into their system, get the mechanics all set up the way you want in their system so it can finally do it. And what you'll find pretty quickly is that what they do is they give you very standardized systems. Here's a rotary axis. Here's a rotary axis with gearing. So they might actually be able, to do the system I'm going to draw. Darn it. So here we have, this is our arm. And I don't know, should we put a mass on the end, or that's the gripper, something like that. And now if we want to turn this, let's do some simple gearing. Generally, you would use a gear head or direct drive, but we'll do a simple gear. We'll attach a gear here. And let's attach another gear here. Because we're trying to deal with that problem of high speed, low torque motor, yet out here, this mass is not, this arm is spinning at what? What would be the approximate rotational velocity of this arm? Revs per second. If it went 1 rev per second, how fast would that be? How fast would that robot be moving? 1 rev per second. I mean, that'd be throwing frisbees at 1 rev per second, right? That would be if a robot arm was going 1 rev per second, which is 60 RPM, you'd be standing back from that thing. That's fast. However, a motor, the standard motor, the little DC motor that you could buy that's the right power range for it, probably is around 3,000 RPM without any problem. So here we have an arm that wants to move 60 RPM, and that's too fast. 30 RPM might be our maximum speed, but yet we have a motor that we're going to attach, and we're going to tap. Let's just keep drawing. We'll attach here. So we'll put shaft here. We can weld this together right here. We'll just consider that welded for today. Bad design, but whatever. And we'll put in a coupler and then we'll go to the motor. And the motor comes with the motor shaft. So here's our motor. Why do we have to put in a coupler? The reason we got to put in a coupler is because this gear here, I drew a gear in the air. You don't get to design gears in the air. And if you just put a gear on the end of a stick, that's not going to work either. So this gear really has, the shaft, and has a set of bearings over here. The shaft isn't in the air. You don't just spin a shaft in the air, right? So essentially at a minimum, you have fixed, and in the motor, you also have, simple. You also have a bearing and a bearing. You start to line up bearings, and as you start to have parallel misalignment, axial misalignment, angular misalignment, because you decided to go ahead and use a piece of sheet metal for your motor mount, right? And it was weak and it wasn't quite at 90 degrees, but SolidWorks said it was plenty strong, right? And it is, but it's weak and it's not necessarily, you didn't quite get 90 degrees. So you're really putting in a coupler here to make it so that your tolerances don't have to be as perfect, because they're not gonna be, right? Especially because you guys are all making the first one of something. If you moved on and were making the 100th one of these and the 1000th one of these, all of a sudden you're gonna have things in place to control a lot of different variables, but you're making one. And that's the way it is. So we need a coupler in here. And the tricky part of that coupler is that coupler has to transmit torque, but it can't be a spring. Okay, so these are our issues that we're going. So now let's go ahead and we need to write the formula for this. So overall torque to accelerate equals. And here we go. So the kind of the way that I would do this is in two parts. One is to analyze kind of how the inertia reflects back to the motor. So this inertia out here has some things as it reflects and comes back through the mechanism. This is a simple mechanism. It's rotary to rotary. They get only more complicated than this. But we know we're going to have 1, 2, 3, 4, 5, 6, 7 terms, 7 inertias that we got to deal with. Some matter more than others. The hard part about this is you don't know which ones matter until you actually get the numbers out of the equation. You could guess at which ones matter, but you can guess wrong pretty easily here. So we got to write the whole formula correctly. And this is the I part of the I alpha, and somewhere way out here, we're going to have alpha. I don't think our 7 terms are going to fit in that, but let's see what happens. Okay, so there's a couple little rules here that I've developed to help you figure out these inertias and how they appear back to the motor, because gearing changes things and inefficiencies change things. And a minute, when I say things, I mean the torque. We could start this formula with I equals, but I actually found it easier to put I into there and actually calculate torque and do 2 things at once. Because remember, when I developed the system, I was actually trying to make money with the system. So when you try and make money with something, you need 2 things. You need it to be fairly quick, but you can also never be wrong, which is a weird concept for students to get. In 6 months when you graduate, you guys don't get to be wrong anymore. If you're wrong too many times, you're not going to be doing that anymore. And so when somebody's paying me to do motor sizing, you had to have a system that gave you the right answer. And also, I guess the third thing in there is I'm giving you a system here with just physics, but it's kind of enough of a system so it can be checked by somebody else. And you'll find that this system is everywhere in the motion control industry. If you kind of follow this procedure, and there's other ways to do this, you can come at it from an energy standpoint, you can come at it from power, you can come at this different ways to get to the motor torque and, you know, select a motor. But in general, this has been around long enough now. It's the system. For a long time, I didn't publish this handbook, and then finally it's like, all right, everybody can have it. And so there's thousands of engineers that know how to do, and if you want it checked, you got to do it this way. Otherwise, we all have to figure out your system first and then check your thing. So thus, here we go. So rule number one with this is start with the inertia that's the furthest away from the motor. And we're going to work backwards and we're going to list them, because every single term gets simpler and simpler as we get back towards the motor. So in this case, the inertia is that one. And we'll call this, so we need some labels, right? So we will label this, we'll call this mass. That's the mass. So as odd as this sounds, I'm going to write this inertia of mass. Okay. Later on, we'll actually go figure out what is this inertia of here, and it's going to be an mr squared proposition. Sometimes it's the integration, but generally we can model things as one of three things: point mass, solid cylinder, or hollow cylinder. So we're either going to be doing point mass, solid cylinder, and actually all a hollow cylinder is two solid cylinders, one subtracted from the other. So for instance, when we come back to this mass, yes, that mass, some of it, if this is, let me just draw here, if this here is its rotational point, and that's R, and we know that point mass is mr squared, right? Essentially, that's the easiest one. We don't have to do anything. If a point mass, mr squared, boom. And so here we have R, there you have M, boom, you know the point mass. Now technically, that is not a point mass. Some of it is a little further away than others. There's, in fact, I guess technically there is no such thing as a point mass, right? You really wanted to get, is there? No. Maybe the quantum physics guys would say, yes, there's a point mass. But that quantum physics is where I decided that physics was not going to be my major. So inertia of the mass. And in this case, later on, we would say, we would come back and, you know, after we get this formula written, we've got to come back and say J mass, what that is, so that we can kind of plug it in to this. But that's the second step. The first step is get the overall equation, and then the second step is write a little bit more equation. So in this case, it'd be mass times radius of the arm squared, right? That would be how that one would be. Now, the reason I drew this in the numerator means that there's a denominator. And in the denominator, you're going to put two things. The two things that go in the denominator are inefficiencies and gear ratios. That's what goes in there, because we are calculating torque, not inertia. This term is I, right? That's what this term is the I term. Okay, so here's where you, oh gosh, there's always movies. The original one was Honey, I Shrunk the Kids, and then there was, you know, pick any movie where the people are really little and everything else is really big. It's all scaled. There was downsized. There was, I don't know, what's the latest movie where the people are tiny and everything else is big? You know, pick one, right? So I actually, as goofy as it sounds, the easiest thing for me to do is visualize me running around on the machine. So now I'm going to start here, and I'm going to run along the machine. And I got to look for two things. Any place there is a discontinuity in velocity, meaning I'm jumping from one thing, kind of like getting on an escalator. You know, when you come up to an escalator and you're going and the floor's not moving, but it's moving, there's a discontinuity there, and you got to go from one to the, got to jump at it to make it move. There is an inefficiency. Guaranteed. From the motor's perspective, you have two things that are moving at different rates. There's an inefficiency there. The next thing that you're looking for is gear ratios, because that changes the inertia significantly for us. So let's walk along here. So we're the mass. First thing we do is we'll jump down onto the arm. So was there any discontinuity there? Are those two moving the same? They're moving the same, right? In fact, here's another way to think about it. If you could weld the mass to the arm, for the most part, if you got out your welder and you tack a weld on it and it still worked, then there's no, sometimes this sounds stupid, but sometimes you're going to look at things and it's like, boy, are those the same? You're going to have some weird systems. And so it's like, can you weld it together and it still works? Yeah. Okay, then there's no inefficiency right there. So nothing happened between there and there. So now we're moving along the arm. We're going to run along the arm. And we're going to come down, and we need to jump down onto that gear. Okay, any inefficiencies there? Could you weld them together? Yep, okay, nothing yet. We don't have anything to put in yet. It's all just, now it's really components bolted together, but okay, so now we're going to move from this gear to that gear. Aha. First of all, in order to jump from gear to gear, you're going to be doing that escalator thing, right? It's like getting your jump. Got it. Right? Oh, I know what it is. I know what it is. I'm playing the wrong thing. We need to play Ninja Warrior. That's what we need to play. This is American Ninja Warrior. Okay, so now we're going to jump on from that gear to that gear. Gear ratio. So that goes in here. We need to define that. We'll just say, let's see, G2, G1. We'll say N is N of the G. Since there's only one G in this, we'll say NG is G2 over G1. All right. And so we'll put that in here. N of the gearing. And I only see one gearing in this, so I don't have to define which one it is. We'll just call it NG. However, that's not done. We get to put this squared. Inertia gets reduced back at the motor by the gear ratio squared. And that's a really good thing for us. So that makes this mass, as you increase gear ratios, which you have to do with hot dog motors to get that balance of speed and torque, from high speed, low torque to the opposite, you need gearing. And whenever you do that gearing, that makes this mass look smaller inertia-wise to the motor. So, and it makes it by the gear ratio squared. You probably didn't get that proven out to you, but it's not, if you just say power in is power out and work through, you know, torque times speed and torque times speed, and then work through pretty soon you'll get to the speed of this gear and the speed of that gear is the gear ratio, and you'll get to, oh, it's the gear ratio squared. So you can derive that, not too difficult. Gear ratio squared. Okay, so now we're on that gear. Now, let's jump, and we recorded that. So now we're going to jump from that gear to the shaft. Anything there? Going the same velocity, aren't they? How about the shaft to the coupler? Now there's compliance here, but that's, I mean, you could weld these together so far. Actually, we're done. That's it. That's the term. Oh, no, it's not. we jumped across that velocity. We forgot to write something down. What did we forget to write down? There's one more term that goes in here. What did we forget to write down when we dealt with gearing? Gearing has, we're looking for two things.
The ratio.
And we got the ratio.
Efficiency.
Efficiency. So let's just put that in. Efficiency of the gearing. Now, efficiency of the gearing is probably like these kind of gears. It's probably about 0.9 to 0.95. You know, a chain is 0.98, a belt is 0.9, ball screws are 0.8. You know, they're generally fairly high because they're, but as soon as, for instance, if you went to a worm gear where all of a sudden you have sliding friction in a worm gear mechanism, your efficiency of a worm gear might be 0.4 because you lose a lot of heat in that gear. So all of a sudden it brings up the idea of designing to not waste all your motor's energy on heat. Let's design a system that when you have motor torque or motor power, the energy that you're putting into amps, whatever you want to call it, that most of it is actually going to move the motor or the mass that you want to move. The trouble is, this is what we want to move, but really to do it, we got to move that, and that. But all we really wanted to do is move that. The thing is, when you're designing machines, this happens all the time. You end up designing a machine to move that mass. You're starting to think about design now as you go through this because you're starting to see the inefficiencies in the gear ratios. So let's do this. Shorten that up a little bit. Plus. All right, what's our next one? Next inertia is the inertia of the arm and a denominator. Now, the inertia of the arm, what's the inertia of this arm? You go look it up. It's going to be a solid rod or solid rectangle or whatever shape it is, pivoted around this end. You go on to Google or you go back in your physics book and you look up and it's ml squared over 12. Oh, okay, there it is. So inertia of the arm is, I don't know, some r squared over 12 times, some formula. You look it up. If you can't look it up, you estimate it. Half the time I would say, oh, it's a point mass centered around about that point. That's good enough. Remember, estimations are good because you have mechanisms that are going to change, masses that are going to change, and you can go back and readjust this anytime you want. Once you have the formulas, and the formulas are right, you can go back and redo it. So most of the time you're estimating on the first couple passes. Your design isn't going to be finished for quite a while. But it doesn't mean that you can't start out and estimate, I wonder how big that motor is going to be. I don't know, let's do an estimation motor sizing, and you do it early. Later on, you could really dial it in to get just the right motor. But for now, this is really an estimation anyway, because do any of these components actually exist other than in SolidWorks? No. Sometimes you get a machine where you go out and you're retrofitting it and they're already there. But half the time when you're doing that, you don't want to use those components anyway because they did not minimize that term. They just made it work. And all of a sudden now you're doing motion control. You are trying to minimize inertia and maximize stiffness. Okay, I'm on the arm. So let's play Ninja Warrior. And we don't care about the mass of the arm. It's actually, let's see, welded. Aha. Efficiency of the gearing and NG squared. Well, now that's interesting. They have the same denominator, don't they? So go back and look at the drawing. Should those have the same denominator? They're different inertia values, but the fact that they have same denominator means that, yeah, they both got reduced by the same gear ratio, and they both are going through that same inefficiency. And since they could have been welded together anyway, yeah, that makes sense. Okay, so I wouldn't really look ahead. The first pass through, I would end up with 7 terms and not try and later on you can, put that and those two, the mass and that in the same term, but let's not do that for now. Plus. Next one is inertia of G2. Well, inertia of G2 is pretty easy, isn't it? It's a solid cylinder. And then you can decide, oh yeah, but it has a shaft in the middle. All right. What's the inertia of the shaft compared to the overall inertia of the big gear? It's R squared, right? The inertia of that shaft is almost irrelevant compared to the gear itself. You could ignore it now and just call it estimation. You could treat it, if you knew it was a 1/2 inch shaft, you could subtract it out and make your formula bigger. But for now, well, that's inertia. And well, wait a minute, what do we do here? Inertia of that gear. Well, in order to get from that gear to that gear, you've got to do the ninja jump, right? That means that for gear 2 to turn, it turns after an inefficiency. So therefore, and it turns after the gear ratio, doesn't it? We go across gear ratio. Just what? NG squared. Huh, there's another one of those. Same exact. Okay. This is how you find out. And then J of the shaft. And I'll let you kind of do that. And gradually, J of the shaft, J of gear 2, gear 1, J of the coupler, and J of the motor are what you have to finish up, right? And as you move down this, you find, in fact, we already find it. If we're going to turn that gear, are there any efficiencies you see by you already jumped from here to here. So now we're on this gear. Any inefficiencies between going to there? Nope. There? Nope. No inefficiencies. Any gear ratios going down this? Nope, it's direct driven. So pretty much there's nothing left in the denominator on the rest of the terms. They're all direct drive terms. That's nice for your formula, but that's actually bad for the motor, the overall system, because these things got reduced by the gear ratio squared. These are direct inertias to the motor and have to be turned. Those are the hardest inertias probably to turn. I'll bet you in the whole system, if I had to guess, I would guess that that gear is your highest inertia value when you went to plug in numbers. In other words, another way to think about it is you just did a whole system and you wanted to move that, and you bought a motor that mostly moved that, which is the challenge. You can't get away from that necessarily, but that's why you switch over to, for instance, if you're doing this in the real world, you would move that, you would do this. Oops, what the heck happened there? Undo. You would do, a gear head. Would be preferable. And the reason you would do a gear head is a gear head, you buy it, has predictable tolerances, predictable stiffness, predictable backlash. That's, the manufacturer gives you those things, but it's a series of gears, and the first gear that's on the motor is tiny. And everything after that, all those other gear passes in order to get to a 50-to-1 gear ratio, which really, if you think about this, and you're really trying to make this out here turn 1 rev per second, and this motor turns 30, you're looking at a 30-to-1 gear ratio somehow. Are you going to have a 30-to-1 gear ratio between these two gears? That means this gear has to be 30 times bigger than that one. like, okay, that's not realistic. And so gearing, for the most part, no, we don't do that. We buy gear heads. We pay the money, buy the gear head, and then we get little gears, and this gear head then adds almost zero inertia to the system because the first pass that's directly connected on the motor is a tiny little gear that doesn't have to transmit much torque. And everything after that is reflected through the gear ratio. So, okay, let's stop there. And next time we'll come back and maybe do the friction, gravity. We still have to do an important one. We still got to do RMS. We're doing peak right now, and a lot of systems we've got to figure out overall an average. I hate the word to use that word. I'm going to use RMS because it is not the average amount, but it is related to how much heat the motor is going to have to dissipate. So some systems we got to go back and do this RMS calculation, and it's horrid. But at least we have it's an easy formula. It's just big to deal with. So let's stop there. I've offered to your classes to give you that, get rid of your project paralysis, so to speak. If you need help, schedule a Zoom meeting. And the one thing that we're going to need is we're going to need to see some written specs of you as best as you can do. They don't have to be perfect, but written specs with tolerances and conditions. And if you've got some specific design ideas you want me to go over, we got to get the sketches in front of us somehow. So one of you will be sharing some initial sketches or something so that we have something to talk about, because this hand waving stuff won't work too good. But you're welcome to schedule those starting anytime.